Now let's talk about Mitsubishi electric inverters. So today we will go into detail about the range of inverters offered by Mitsubishi Electric. So let's see in detail all the models with their different particularities in such a way to be able to understand how to choose one inverter rather than another. Therefore, given the premise made previously on a general explanation of what an inverter is, what it does, and what are the problems that arise when installing an inverter, independently Mitsubishi Electric or not. Now let's look at the Mitsubishi Electric in detail. In this slide, we can see this table where we can go to determine the inverters currently available, sorted based on performance and sizes in kilowatt. Starting from the bottom, let's see our entry level FRD700. It is the basic model, it is very compact and allows you to carry out the main basic management of an asynchronous motor. It is necessary not to be fooled by the fact that he is an entry level or that he is at the lowest level in terms of performance, as he is also highly appreciated by our customers as he does his job at his best. Just above we have the FRE700, very similar to the FRD700 but with more features. To then follow that new model recently released on the market, the FRE800, and then go on to follow with the FRF800, where we see outside of the performance, obviously superior to the FRE800, sizes in kilowatts that are clearly higher. So if we think about large size motors, the choice of underlying inverters is eliminated, but you necessarily have to move on to the next one. Finally, there is the FRA800, which is our top of the range. FRD700. How to understand which inverter we are talking about from its sides? With the inverter code, you can understand everything. So you can know which inverter we are talking about, its size, and so on. Let's give an example in detail. FR indicates that it is a Mitsubishi electric inverter. D740, this acronym can be broken down into D shows me the model. So we have D model, E model, A model, and F model. After the letter, these three digits follow, which indicate different aspects to me. The first as if it were the release date. So as this figure grows, it means that the model is increasingly recent. After this number, we have these other two digits, which indicate the power supply network and therefore the supply voltage. We have the 40, which indicates that it is a three-phase 4000 volt power supply, rather than the 20, which indicates 230 volt. The 20 can have two variants, with or without S, where 720S indicates to me that it is a single phase 230 volt. The number 20 without S indicates that it is a three-phase 230 volt. Then we have these three digits that define the sites. In fact, they represent the nominal current of the inverter. This 036 indicates to me that it is a 3.6 ampere. In fact, in all of our inverters, To understand the final current, you just need to put a comma between the penultimate and the last digit. Then we have a further symbol which may or may not be present. Generally in Italian products there is SC, which indicates the connection logic of the safety circuit. As all our inverter already have a double safety channel on board. SC tells me that the safety is with the positive logic source. So bring a 24 volt positive signal to the safety channels. Below we see the tables where we can go to see what the available FRD sizes are, also obviously based on the power supply network. As regards the FRD 720S model, therefore 2230 volts in a single phase, we start from a minimum of 0.8 amperes, which correspond at 100 watts, up to a maximum of 10 amperes, which correspond to 2.2 kilowatt. As regard instead 4000 three-phase volt, we have 1.2 ampere, which correspond to 4000 watt, up to a maximum of 16 amperes, which correspond to 7.5 kilowatt. The FRD 700 inverter has several highly appreciated features, such as open loop vector control, which allows you to obtain 150% of the torque at 1 Hz, which would be unthinkable for a three-phase asynchronous motor in V on F control, because it has low voltages at low frequencies, and therefore, since the torque is also given by the square of the voltage, I could have a low torque value. Output frequency up to 400 Hz compared to the nominal frequency of a motor which is in order of 50 Hz. Integrated 400 watt braking chopper to dissipate any excess energy. From 400 watt upwards, because below it is not possible to move excessive inertial loads. Side by side mounting 40 degrees, so they can be placed side by side with minimum distances, but with a maximum of 40 degrees centigrade inside the panel. Safety stop, safety torque off, therefore double safety channel input with the function that safely disconnects the power section and therefore the motor. Very comfortable spring clamps, includes an onboard serial port for Modbus RTU or Mitsubishi protocol with the RJ45 connection. It can be integrated with a PU, can be integrated with a dial, so the screen with a wheel. Energy saving function, there is a parameter with which this function can be activated, but to use it is necessary to carry out analysis, since if there was a variable load, the energy saving function would not be suitable, as it could create oscillations. Overload 150% for 1 minute and 200% for half a second of the nominal current. This is important because, for example, to lift a vertical load, the This connection force will require a current higher than the motor nominal, and therefore it could get close to the inverter nominal, and this function allows you to go further to overcome this force to move this load. The connection diagram shown in this slide concerns the power section. L1, L2 and L3 for three-phase power, rather than L1 and L2 for single-phase power. Between P1 and P-add, you can mount a DC inductance, obviously by removing the jumper. The harmonic content is proportional to the size of the inverter itself. The inductance must be mounted on inverters larger than 75 kW. An external braking resistor can be mounted between PAD and PR to dissipate energy. U, V, and W are the motor output. Let's now move on to signals. All our inverters share the same signals, and by improving the performance of the models, we will have more signals, and therefore this will remain basic. STF is start forward, STR is start reverse. RH, RM, and RL are three default speeds to start the motor at a certain frequency. RH is the high speed 50 Hz, RM is the medium speed 30 Hz, and RL is the low speed 10 Hz. Obviously, to start the motor in rotation, two signals are needed. The direction of rotation, therefore STF or STR, and speed reference, therefore RH or RM or RL. Obviously, all these speeds can be parameterized as desired. Inside the inverter, there is also a 24 volt power supply where PC is the positive 24 volt and SD is the common, therefore 0 volt. In fact, in positive logic, I take the positive from the PC to close the different signals. If an external 24 volt power supply is used, it will be necessary to connect the 0 volt of the external power supply with the SD so that the signals can be correctly read. Our inverters can be driven either with digital speeds or via analog references. There are two analog inputs that are the terminal 2 and the terminal 4. The terminal 2 can read from 0 to 5 volt or from 0 to 10 volt. Instead, the terminal 4, which by default is parameterized to read a current input, can be used after parameterization and moving the microswitch to voltage to read a voltage signal. The pin 10 supplies a 5 volt and the pin 5 is the common. So as if there was another additional small 5 volt power supply. You can see below an example of potentiometer wiring. Still talking about inputs, we see the safety SC is a 24 volt positive, and by default it will be supplied bypassed as a double jumper, which will end up on S1 and S2. and the 0 volt is always the common SD. SD is the common reference for everything digital, while the pin 5 is the common reference for everything analog. Now moving on to the outputs, there is A, B, C available, which is a relay. C is the reference common to which I will bring the power supply. A normally open and B normally closed. By default, it works on the error, so when an error occurs, A closed and B opens. This can also be parameterized. AM analog output from 0 to 10 volt reference based by default on the output frequency 0 to 50 Hz. Finally, there are the open collector transistor outputs. SE is the open collector reference potential. So I will bring a positive 24 volt. Run is the output which will provide me with a positive signal when the motor has exceeded 0.5 Hz, and SO when the safety has intervened. Speaking now of the FR-E700 inverter, it has some more functions than the FR-D700. As far as reading the model is concerned, it is exactly the same concept seen previously. As regards the sizes, the FR-E700 also exists in the single-phase version up to a maximum of 2.2 kilowatt, but the nominal current has been increased compared to the previous model, and the size has been increased to 400 volt three-phase. In fact, before it stopped at 7.5 kilowatt, while now we reach 15 kilowatt. As regards the characteristics here too, we have the possibility of vectorial but advanced control. By open loop, we mean without encoder. It is possible to reach 200% torque at 0.5 Hz. The output frequency reaches 400 Hz. There is an integrated 0.4 kilowatt braking chopper, 40-degree side-by-side mounting, spring terminals, Modbus RTU and protocol Mitsubishi RJ45, and there is USB for programming. First, however, if I had wanted to connect to the FRD700 via software, but there had already been serial communication, I could have to free myself from that communication, define the parameters at serial level to connect from my PC to the inverter and connect me. Here on the FR-E700, it works on separate channels. There is always PU integrated with the dial, and the simple torque limit has been added so as to be able to limit the output torque. There is a 150% overload for 1 minute and 200 for 3 seconds against the previous half second. And finally, the possibility of putting an expansion which was not possible on the FRD 700. The type of expansion is that for an Ethernet protocol. The Ethernet model already exists, so with the expansion. Otherwise, it can be taken later. It will therefore be possible to connect the inverter to the network with the CC-Link IA Field Basic Protocol rather than Modbus TCP/IP. As regards the connection diagram, I wouldn't dwell on it too much, as it is very similar to the FRD 700. As regards the signals, it is identical with the addition of the res, so the reset. In fact, if the inverter goes into fault, it is possible to do a remote reset, which is not possible on the FRD 700 by default. What can instead be done is to sacrifice an input was then parameterized to have the reset function. As regards the outputs, an output has been added, namely FU, which is an output that is activated, giving me a positive signal when I reach a predefined output of 6 Hz or more. It is usually used to release the brake. I could put 1 Hz so that the motor starts pushing, and then let's go off the brake. Let's now talk about FRF800, which is dedicated to pumps and fans, as it has particular functions for the latter. The code of this inverter is always read in the same way, with the difference that the European or non-European model is defined by a 1, which will be found at the bottom, and by a 2. In fact, in the case where is present the number 1, this number is preceded by the sites in kilowatt, whereas the number 2 is preceded by the sites in current. It already exists in Ethernet mode by default. The range of sizes has been greatly expanded. As regards 200 volt 3-phase, as single phase is not possible on this model. Single phase connection is still possible, but there will be a derating of approximately 30% of the nominal power. The sizes are those shown below. There are also special versions of FRF and FRA. It is clear that they are a special version due to the fact that after the digit that indicates the power supply, there isn't the number 0, but another number. In this case, the number 2 makes me understand that I have a separate conversion unit. With this mode, I can obtain high powers up to 1560 kilowatt with 1212 ampere. FRF is bulkier than previous models. It has working frequencies up to 590 Hz. It is possible to perform offline auto-tuning and then pre-parameterize the motor characteristics such as excitation current, rotor resistance, stator resistance, but all with the motor connected. PM motors can be controlled. It is possible to externally power the control board at 24 volt, so I can parameterize the inverter even without the 400 volt before sending it to the customer. It has an internal temperature sensor, so once a certain temperature is exceeded, this thermal pad switches, sending the inverter into alarm. FR F800 has advanced optimum excitation control for the pumps and fans. Common connection of multiple inverters in DC bus. It has an integrated PLC to program logic that is not excessively complex. It is possible to copy and paste parameters and PLC programs with a USB stick. In fact, there is an opening door where you can insert the stick. Integrated STO, integrated Ethernet communication, CC-Link FIL Basic and Modbus TCP/IP, and there is the possibility of installing up to 3 options for the main communication protocols. Built-in breaking transistor up to 55 kilowatt, then you add an external breaking unit, and obviously, as already mentioned, dedicated functions for pumps and fans. A peculiarity of this inverter is the possibility of selecting the optimal power of the inverter. In fact, a rating is defined where by means of a parameter I can choose between two types of service, light duty or super light duty, based on the load that I will use. In fact, on the table contains information relating to the overload. In super light duty, I will have a decrease of these values as the nominal current will rise. As far as pumps are concerned, there is this very interesting function, namely deragging. Just think of a pump in which there is not only a liquid, but also foreign bodies in the duct. These bodies could block the pump impeller, thus causing problems when starting, as it could try to start but failing to do so could give an overcurrent alarm. This deragging function allows you to define how many times and at what frequencies to push back and forth to unblock the impeller and start everything more easily. Another appreciated function is the monitoring of the operating status to detect mechanical faults. It is possible to activate functions to have the inverter independently create a graph showing torque values at certain frequency values. Once the torque curve has been defined, it is useful to understand if there are mechanical problems. Once the optimal curve has been defined, when I go to read a torque higher than the predefined optimal one, it means that I could have mechanical blockages. Instead, if I read a torque lower than the predefined optimal one, it means that could be another problem, such as in the case of belt pulley transmission or a broken or a slipping belt. A further very particular function is the flying restart. It is useful because after a power failure, the rotation is restarted by exploiting the remaining inertia of the motor. In doing so, it does not stop the motor to restart. It has just think of a very large fan. It would be unthinkable to have it nail it down and then start again from zero. Regarding the connection compared to the previous model, there is a small difference. In fact, in this model, there is the L11 pin and the L21 pin. In fact, in this type of inverter, the power section is separated from the control one. So I can turn on the control board using L11 pin and L21 pin, and then feed the power through L1, L2, and L3. As regards the signals, however, there are new ones, including STP. This signal is used for impulsive signals. In fact, generally, the inverter works with the on state of STF to manage the gear. But if the gear is managed via buttons, it is necessary to wire it to STP, a normally closed button, while on STF, a normally open button. So on the rising edge of the latter, the motor will start. So STP works as a self-retention. Jog is used to perform jog operations, generally at 5 Hz, until the signal is kept high. Then RT is present for the second function section. For example, a second motor, or in case you want to have second ramps. So when RT is active, it is like doing a changing recipe of parameters. However, it will be necessary to fill in the parameter of the second function. MRS is used to release the motor by inertia, but it is not safety. AU is to enable analog input 4. So if AU is off, I read analog input 2, while if is on, I read analog input 4. On previous model, it would have been necessary to sacrifice an input to parameterize it, as AU, so once enable, analog input 4 is read. CS is the signal to activate flying start. As previously mentioned, there is the possibility of powering the control board through 24 volt on terminal 24. Speaking of the analog signals, there is the 10E pin. This pin has been added and provide a 10 volt, and there is also a further analog input, the input 1, the pin 1, which is polarized. In fact, I can read more or less 10 volt, more or less 5 volt, and by default it works as compensation to increase or decrease the main value. If through input 2 I am driving at 50 Hz, I can increase or decrease with the input 1 slightly the frequency, therefore to make micro calibrations in the order of a few hertz. In this inverter, there is a double dip switch, one for each analog input, so that both analog inputs can read current and voltage. For safety, by default from PC, the 24 volt is brought to S1 and S2. However, the safety common is released, so we have in common apart from no longer SD but SAC, with which stand for safety input common, which must be closed on SD. At the output, there is a second relay that works like the one previously explained, but by default it does nothing. So if you want to use it, you will need to parameterize it. I have the addition of SU as an open collector output, which is an intelligent output because it is activated when the inverter has made the motor reach the programmed frequency. EPF stands for instantaneous power failure. So it informs me if there is a network failure. OL warns me that the inverter is overloaded. Like AM analog outputs, here it is polarized, so it can give more or less 10 volt depending on the gear. And we have another current analog output from 0 to 20 milliampere and the safety output. We are now talking about the top of the range, which you will see is mainly identical in terms of cabling as in the previous one, but obviously it has some more features. As for the code, they are most identical to the previous one, only the main difference is that the FRA800 inverter is born with the rating, as we said before, in normal duty, so a lower current by default. And then eventually we can also bring it in light duty or super light duty. We can do whatever we want. Another special model we can see it from this figure is the EP55 FRA 846. There is also the FRF 846, where this 6 indicates that it is an EP55. For the rest, absolutely nothing changes. This is an example of a separate unit, as we said before. As for the FRA800, we have the operating frequency 590 Hz in V-on-F control, but there is also the real sensorless vector control at 400 Hz. Real sensorless vector control allows me to work in vector control, but real sensorless, so open loop. But it is different from what we said before about the FRE 700 and so on, with the latter being able to manage the vector control, which in fact is a closed ring, which the FRA 800 cannot do. It is the advanced position control. In fact, we can make real positions, mainly table positions. We can go to manage the PM motors. There is the STO integrated, the external 24-volt power supply, the PLC integrated, the possibility to copy the program parameters with the USB-K, the common connection of several inverters to a DC bus, the energy saving optimum, not advanced like the other. In fact, the energy saving of the FRF 800 is better. It is dedicated for defense. So, in fact, it is advanced, different from this, which instead does not have. The Ethernet connection integrated, CC-Link I Basic and Modbus TCP/IP, the possibility of installing 3 options for main protocols rather than also encoder boards and so on. Transistor and breaks incorporated up to 55 kilowatt, internal sensor, the MC filter that the previous one also had. As for the connection diagram, it remains totally unchanged compared to the previous one. The same goes for the signals, and in fact, I could not complain much. The last one to arrive in the Mitsubishi Electric family is the FRE 800. The FRE 800, let's go back to the compact family. He also been enlarged a little bit compared to the previous FRE 700. The FRE 800 has a particularity. It exists in serial mode, like the previous one with the possibility of digital management with many digital inputs for its management and so on, or in Ethernet version, where the digital inputs are reduced to the minimum, but you already have on board the main communication protocols. For example, if you go to get the FRE800 EPA model, you already have on board multi-protocol, such as the CC-Link IE TSN, which is our new field bus, the CC-Link IE field basic, the Modbus TCP/IP, the Ethernet IP, and the BACnet EP. So already with this model you can choose between one of these protocol rather than going to get the EPB model. You already have the CC-Link IATSN, the CC-Link IA Basic, the Modbus TCP/IP, and the Profinet, or the EPC that has the EtherCAT. The FRE800, unlike the others, supports different types of connections. In fact, the FRE700 inverter with the Ethernet expansion has only one Ethernet port. So you are forced to use an Ethernet switch to be able to connect the different slaves under the hypothetical master, which will be a PLC or whatever it will be. The FRE800 on the other hand has a double port, so it allows you to do both the ring type connection, so the in-out rather than the star type, so a classic switch, and then go to the other dispositives. We have a particular functionality, which is the inverter to inverter link function, that is managing the integrated PLC and communicating the different slaves. So doing so, for example, we can go and pilot the other inverters without the function of a master. If you think about it, because the master is the inverter itself. So I don't need a PLC to go and say this here could be an example of ventilation. I have the main ventilation, and if the temperature sensor goes beyond a certain value, so for me the ventilation done by the first one is not enough, I start the slave 1, which says it is not enough, the slave 2, the slave 3, and so on. We also have the possibility of managing the braking resistance, obviously already available, and the energy saving function. It also has an integrated PLC. It can be piloted in different control modes. In fact, it can be piloted with the classic V on F control mode rather than the advanced magnetic flux vector control mode, which is the open loop vector control of the FRE700, so the predecessor. There is also the possibility of manage the encoder, which on the FRE700 was not compatible. Now I, in fact, can also manage the encoder and, as I said, the PM motor, so the permanent magnetic motor. And this thing here is not a small thing. The possibility of the side-by-side thing I was telling you about, here is an image that already makes you understand what I meant. One attached to the other, so that 40 degrees maximum inside the frame. And then this one coming on also in EP67 models. It already has safety features. It also comes out with the STO in the main versions, but there is the SE version, so the safety version, which has other safety features, such as in addition to the STO, the SS1, the SLS, the SBC, and the SSM. It all works on bus, for example, using the ProfiSafe. Let's now talk about how to manage an inverter. So, for example, parameterization and so on. What you see here in front is the PU integrated with DL, that of the FRD and FRE 700 inverters. Let's understand what it is composed of. Display 7 segment indicator in which you can go and view parameters, values, and so on. Then we have the unit of measurement, hertz, ampere, rather than if it were volts, the last digit could be sacrificed and, for example, a V should be shown. Let's tell you what it is doing. So the run LED, if the motor is running, the run LED has multiple states. Off, which mean that no gear is coming. Fast flashing, which tells you that it is running, so you have given the gear, but there isn't a speed reference. Mon tells you if you are monitoring something, such as a frequency, a voltage, a current, or something. PRM if you are in the parameterization area. So you turn off MON and turn on PRM. Below are the main operating modes of the inverter. PU parameter unity, panel unity, where you will be able to control the inverter directly from these buttons. Run gear control with the wheel. We are going to give it the desired frequency. Stop rather than XT. So all commands will be taken from an external switchboard. STF, as we saw before, STF, STR, RH, RM, rather than the potentiometer, and so on. Or from net, so network. So they are taken from the serial rather than from the Ethernet. It is also possible to make a combination between them. For example, I am in network, but I want the physical gear control rather than I am in PU, but I want the speed control from a potentiometer. I can make the combination as I like. The buttons below are very important because I need PUXT to change the operating mode from PU to XT. What HUD is before, because when you have to parameterize the inverter by default, the latter wants to be in PU mode to accept the parameterization. Otherwise, it will give you an error. So when you turn it on by default, it comes out in AXT mode. By pressing the PUXT button, the latter will go to PU, and from here it will allow you to do the parameterization. Mode is the button with which you can enter the parameterization area. In fact, if you turn on the if you turn on the inverter by pressing the mode button, you will read P0, so parameter 0. Then with the dial you go to look for the parameter you want. With set you will enter the parameter, you will vary its value always with the dial, and then confirm again with the set the value you want. This is the PU of an FRA or FRF 800. As you can see, it looks different, but it's almost identical. The classic display, we have the PU XT and net operating modes with the usual PU XT to change the operating mode, and the concept does not change. The PRM LED if I'm in the parameterization area, like in this example. The P point run LED if the PLC is running, and if we have an induction motor, then asynchronous, we have the EM LED on. Instead, if we have an PM motors, we have the PM LED on. The LED run has disappeared because it has been incorporated into the buttons, and now there is the possibility to drive forward and reverse. So no longer just the green run button that gave a single direction, but I can do forward and reverse, where the LED run is already incorporated. The usual story of the LED incorporated. So the light off is it means that the reason the running, the fast light means that he's running, but without speed reference, and the fixed light indicate that the motor is actually running. Stop, the button stop to stop it. Let's look at an example of piloting modes. So how to control the inverter. First of all, the PU mode. So that to go there, you turn on the inverter, you will read AXT, you press PU and XT, and it will go to PU. You can go and pilot the inverter 100% on PU mode. So you put the rotation of the motor directly from the panel unit. But what do you have to do? By means of the dial, which is this thing where the finger is, you will turn clockwise until it reaches the desired frequency. When it has reached the desired frequency, as this example says, for example 30 Hz, you will press set to confirm the desired frequency. An F will appear that indicates that it has been taken, this frequency. Once you have done this, obviously the screen will return to 0. But why? Because you have not yet given it the start command. So it says, now I am throwing 0, but rest assured that I took 30 Hz as I told me with the F. Once I have defined a frequency, I give it the start command or rater, the sense of rotation, forward, rater, then reverse. When you press forward or reverse, you will see that the frequency will begin to increase until it reaches the set point between you defined. Obviously, in the time defined by the acceleration ramp, which is parameter 7. To stop it, you press the stop button, the red one, and it will stop with the ramp defined in parameter 8, then return to 0. Another mode of operation is the AXT, so the external mode. We have the classic STF or STR gear and the RH, RM or RL speeds. As I was saying you always need two signals to set the motor to rotation by default. Then eventually with the parameter you can with the parameters you can always find some tricks to change the gear and set a fixed speed. But generally you always need a gear to define the sense of rotation and a speed set point. So, for example, by closing the STF contact and closing the RH contact, the frequency output will reach 50 Hz by default. By opening the RH contact and closing the RM contact, it will reach the 30 Hz, and opening the RH contact, RM contact and closing the RL will bring 10 Hz. Another mode of operation is by means of analog set points. So we will simply wire STF rather than STR, and we will wire our potentiometer between 10, 2 and 5, where I remind you that 10 is a plus 5 volts, 5 is the common 0 volt, and 2 is my reference signal. So by varying the voltage, the output frequency will vary from a minimum U set to a maximum U set. By default is from 0 to 50 Hz. All analog set points input and output are calibratable. What does it mean? It means that if I want to define that the signal is not is not from 0 to 5 volt, but is for example from 1 volt to a 4 volt maximum, I can do it. If I want to define that the starting frequency is not 0 but is 20 Hz, I can do it. The same with the maximum frequency. Obviously, instead of 50 Hz, if I want it to be 40, 60 or 100 Hz, I can do whatever I want. Another example is with the analog input 4. As you can see, the AO signal is closed, which on an inverter FRD or FRA, as I said, I sacrifice an input to give the AO function, while on an FRA or FRF 800, it is already present. So I close such contact, I give the sense of rotation command, and I provide a signal that start from 4 to 20 milliampere, which again is 100% calibrable, and I can define the maximum and minimum frequency as I want. Another often used control methodology, which is semi-automatic, is PID control. For example, for a pump, imagine having a pump that must constantly maintain a pressure inside a contact. And so I say to the inverter, you take care of it, you keep the pressure defined by me. This is possible by means the PID functionality, where by means of an analog signal coming from the field, for example, a pressure transducer, usually it is from 4 to 20 milliampere. To give you an example, I will speak from 0 to 10 volts, because I speak of easy numbers. I will have a pressure transducer that is wired directly to the inverter, which will give me a reading reference. Then I will go and define a set point. So the set point is the desired value that I have to keep, and it will correct itself. For example, pump contact, pump and contact. I want to keep 5 bar in the contact. The sensor, the pressure transducer, is a sensor that reads from 0 to 10 volts, which correspond from 0 to 10 bar. So hypothetically, I would like to keep, since I want to keep 5 bar, the hypothetically 5 volt, which are 50% of the input signal. I then go and pat a set point as a parameter of 50%. I wire my signal, I enable the PID, telling it that I want the reverse functionality, because it is reverse, because obviously, being the contact, what does it do? By increasing the pressure, I decrease the frequency. So I make the reverse option. So when the signal increases, I have to decrease the frequency to pump less water. For example, to reduce the pressure inside the contact. When instead the pressure drops below the set point value, I increase my frequency again to increase the pressure to the desired value. The direct function exists, of course, and one example is the second. I have to keep a temperature. For example, I'm wired, maybe I'm going to manage ventilation. If the temperature sensor increases, the temperature is raising. So I have to increase the output frequency to try to cool it down as much as. A classic example could be this. You see a pump pressure transducer which is connected to input 4. In this case, with the active PID, no AU enablement is needed. It is already enabled in autonomy. So when I enable the PID, it is as if input 4 was already ready to read. Input 2 becomes a variable set point, or you choose the set point parameter, so you put a fixed value. Otherwise, with a potentiometer based on the input value, you define a good variable percentage. And then there are different functionalities of the PID that I am not going to go into too much detail. Maybe if you like, after you have followed this course, maybe you will go into some more detail. So I always recommend that you contact our technical support, which will give you all the detailed information about it. Anyway, just think that there are different functionalities of the PID. For example, the automatic frequency of habilitation. So under a certain frequency, normal work. When I exceed it, it activates autonomously. The reverse function rather than direct. Set point, the possibility of modifying the earning. So proportional earning, integral earning, and differential earning. PID lower limit, PID higher limit, the possibility of managing such signal also through communication rather than enabling the sleep function. So if I am below certain frequency value for n seconds, I fall asleep. In the true sense of the word, the motor is left to run, and when it is requested again for operation, it starts again, and so on. But I would say not to dwell too much on this part here. Now let's talk about regenerative energy. At the beginning of the course, we saw the question of braking resistance. So braking resistance that comes to me when I have energy dissipation problems. So maybe braking where there is a load with a large inertia rather than being dragged. So with vertical loads that must be maintained in their descent. So when I have this kind of problem, I can use different methods to avoid errors. Because let's say that my worst enemy is error, because if I want to brake in a controlled way over time, the inverter must not give me an error, because if it gives me an error, the motors is left to run, and maybe I could do damage. So what can I do to avoid this problem here? I have three main ways. Really four. In the reality, there are four main ways. The first is to extend the deceleration time in biblical times, even if it is not always going to solve it. In fact, very often it doesn't. Then maybe I need a very short time, and in fact is for this that there is this problem. Otherwise, the other three solution could be to use a particular function. One of these is the regeneration avoidance, and are present in all of our inverter, and I will explain in the next slide. There is also the possibility of increasing the magnetic excitation during deceleration. So I'll give you a hand precisely from magnetism to break the tree, rather than using braking resistances or external braking units. The first is regeneration avoidance. Regeneration avoidance is a function that allows you to avoid the inverter making an error. What does it do? Basically, regeneration avoidance self-corrects the output frequency to try not to make an error. The simplest example is that of deceleration, which is the most common one. So in the graph above, we see the DC bus voltage. In the graph below, instead, we see the frequency output from the inverter. We are going at a constant frequency, so the DC bus has an almost optimal value. I try to decelerate, so I go to reduce the frequency. When I go to decelerate, the DC bus voltage begins to rise vertically. Once I reach a certain threshold, which is then defined in parameter 883, but in the next slide I will explain all the parameters, I go beyond the threshold. What does regeneration avoidance do? It gives me a little bit of frequency, because if I'm pulling the load, I don't regenerate. If the load is pulling me, I go in this sort of regeneration. So I give a little bit of frequency so that the load doesn't pull me anymore, but I'm always pushing the load. Obviously, the DC bus voltage goes down below the limit value. So I try to break again. It goes up again. I give a little bit of frequency gain so that it goes back below the threshold value. I try to break again. It stays below. I break. I stop. This function is very useful, because I can, in fact, brake without disengaging the motor, without making a mistake. But there is a but. In fact, the ramp itself is controlled because the motor never lets go, but it's not controlled over time because you understand that this variation, so the frequency recovers, lengthen the ramp in all respects. So it's a controlled ramp, but not controlled over time. And it can also be variable in the sense that it doesn't necessarily have a perfect cadence over time. I told him to do it in 10 seconds. He says 15, maybe it can be 14, it can be 17, it can be 12, and so on. So it's controlled but not controlled over time. Such functionality also work in acceleration, constant speed, or deceleration. Or this function can always be enabled. The parameters for its activation are as follows. With parameter 882, I can enable it. With the value of 1, this function is always enabled. With the value of 2, this function is enabled only at constant speed. The parameter 883 is that threshold we were talking about, which by default is 760 volt DC for the 400 volt power supply, while is 380 volt DC for the 200 power supply. To get the DC bus value that usually rotates inside the inverter, you just have to take the power supply and multiply it by the square root of 2. With that, you get the normal value of DC bus voltage that rotates inside. These are the thresholds for the intervention. You can vary your performance to make it intervene first and so on. The parameter 884 is the sensibility with which it must respond to any. So I vary this, the value of this parameter to have a lower sensibility rather than a high one. The parameter 885 defines the maximum frequency that can be delivered as compensation. So I said take a little more frequency, okay, but how much? By default, it's limited to 6 Hz. If you want, you can go even higher and then possibly again. The other one is, as I was saying, to increase the magnetic excitation. As you can see here, you can see how it works well in the graph. To come to my help and then be able to break the motor. This function helps me, and I could also, and it could also be put in combination with regeneration avoidance to be able to avoid making a mistake. On the option number 1 in quotes, to make sure that if you have to refine a time and the time must be breaking resistance. Throw away in the true sense of the word with the extra energy that you don't need and only bothers you. So Joule effect, heat up resistance and throw away with the extra energy. As far as FRD and FRE are concerned, the wiring is as follows between PAD and PR. As far as the FRA and FRF inverter is concerned, if also FRF800 between PAD and PR. Up to these sizes in the resistance must be mounted between P3 and PR. For its activation, it is very simple. Parameter 30 at value of 1, which I call connected to an external breaking resistance. Parameter 70 instead giving by a calculation, that is the power of the resistance expressed in watts divided by nominal power of the inverter in watts percent. Such value I am going to set in parameter 70. This is an example of a combination of resistances defined by Mitsubishi Electric. In the models above 55 kilowatts, there is the possibility of installing an external braking unit. This external braking unit is very useful because it allows you to dissipate 100% of the energy of the nominal power against the difference that FRD and FRE 700 could reach up to a maximum of 30% continuous as dissipation power, while with the unit you can reach 100%. The FRF 800 and the FRE 800 on the board end already allows you to dissipate the 100% by default. The external unit, which will also be equipped with a braking resistance, is wired directly to DC bus, so between PAD and N less. Before the arrival of the FR800 series, which already allows you to dissipate up to 100% of its energy, there was the FRA741 inverter, which was the regenerative one, up to 100%, from 5 to 55 kilowatts, and in fact it was perfected for crane lifting, moving stairs, and it allowed all types of cycles. In fact, it was nothing more than a composition of an A700 plus unit plus the resistance, and here is our inverter with also energy saving function. Another option could be to use the common DC bus, also for a limitation of energy saving, where you use an FRXC, which is nothing more than a bidirectional converter, where it converts from AC to DC and powers all the inverters directly in DC, and if there were any regeneration problems and therefore the voltages goes beyond a certain value, it reconverts from DC to AC to put them back in the net. I won't go into too much detail here, but these are details that you might want to know when you're interested in the configuration possibilities for the external unit, the A842. Let's talk about the software now. FR Configurator 2 is the software for configuring our inverters. Generally, for all inverters from the A700 series to the current ones. With the software, you can do a lot of things. You can go and convert parameters, so maybe you have to do a revamping. You connect to the old inverter, read the parameters, you do the auto conversion in the new model, and it takes the lead in terms of autonomy. You can go and configure the inverter directly from the software. You can go and read the parameters from the USB key. because maybe you went to a client who had an inverter, but you didn't have a computer while you had a USB key in your pocket. You read the parameters, you take them to the office, you plug them into a computer, and you can already pre-configure and do everything you need. You can also do graphics with the history, so you can edit the graphics. You can go and read the fuel history, so all the alarm, such as the frequency, the current, the what voltage came out, when it came out, how many hours after the power came out. There is also the possibility to use SLMP functionality, mainly to be able to connect to the software. In fact, you have to keep in mind that you can connect to the software, that is from software to inverter in different ways. You can connect via USB cable, which is certainly easier. You can connect via serial, for example, in the case of FRD 700, because for others it would not make much sense to get a stomach ache to connect via serial rather than via Ethernet. So by connecting via Ethernet, you can also go through PLC for connecting. For example, you have installed PLC inverter communication. You can easily connect to the PLC, which will take you from the bridge to connect to the inverter. As I was saying, the FRF, the FRA, and the FRE 800 inverters have already brought an integrated PLC, programmable in a classic way, standard with the classic programming languages. For those of you who have already had experiences with our PLC, let's say that it seems to use GX Works 2 mainly. Let's go and manage the input and output as if it were a classic PLC. You see the input STF X0, STR X1, and so on. We can also go and manage the inverter functionality, change parameters, make them change speed rather than pilot an output, and so on. I can really do everything, but remember in the limits of decency, because yes, it's a PLC, but if I must be done with extreme logic, I recommend an external PLC, possibly a small one. I don't need the most powerful one with an extreme CPU. A small PLC that can certainly be a support and help. Here too, there are a series of SD, so special variables, but I'm not going to list them all in detail. This is also a topic that, in my opinion, must be addressed if you are interested at that time. You can write us an email or call us, and we will discuss it in detail. Copy of the PLC project on USB, but also some parameters, the same thing. You insert the USB key into the dedicated port, the USB A text will appear. By pressing set, you will do mem. By pressing set, you will have memory copy. By turning the wheel, you select PLC program, you go and do the reading, the writing, the verification that what you already have in the key is the same as what is contained in the PLC. Now let's go into the details of the control modes. As I mentioned at the beginning, the inverter is born in V on F, so with a standard control. There are other control methods that revolutionize this control methodology, which are the general purpose magnetic flux vector control, which is a vector control from the open ring, generally managed by the FRD inverter, which is the simplest one. Otherwise, there is the advanced magnetic flux vector control, which is the advanced one, which already allows the FRD and FRE 700 inverter and all the others to be made. Once the advanced magnetic flux vector control is done, it will allow you to switch to real sensorless vector control available for FRA800 and FRE800 inverters, not for the FRF800, and the closed ring vector control for the FRA800 and FRE800, with which we get really high performance. We said that V on F is a standard line that keeps the frequency voltage ratio constant, 1:1. Sorry. But notice from this graph that there is almost an offset at the start. As I said before, since V on F trying to keep the torque characteristic constant has a very low frequency, the torque could be approximately zero. And this is a problem for a synchronous motor. So I'm going to falsify the starting voltage by putting a real booster. In fact, it is called a torque boost, which is parameter 0, which is a percentage referred to the nominal voltage. This extra voltage allows me to start with a torque that is clearly higher than the actual one. So at least I can avoid this classic problem of a standard graph of a synchronous motor, but it occurs to do attention because these parameters may brings some problems. If you use it in the right way, you will be able to obtain higher torque values, and therefore maybe it's fine. If, however, you dare too much with this torque boost, given the classic Ohm's law, you will have a really high current rise, and therefore you will have to deal with other problems. So, other current error. So, use it with cognition. The set value is from 0 to 30%. If the torque boost was not enough, I would immediately recommend you to use a vector mode, such as general purpose, which is a simple vector control mode where the vector product between the excitation current and the torque current is given, which is then defined in a procedure called auto-tuning. So, to do auto-tuning, you have to pre-parameterize the inverter with the motor data, such as nominal current, motor technology, the kilowatt of the motor, the number of poles, the nominal frequency, and the nominal voltage. The number of poles is not defined in the FRD inverter, and you will understand that the number of poles is what unlocks the advanced vector control. Once all the parameters are defined, I perform this auto-tuning procedure, which is automatic. In the FRD inverter, it is static, just like in the FRE 700, but in the FRE 800 and in the FRA 800, for example, it is also dynamic. So you can put the motor in rotation during this auto-tuning procedure, where we get information such as rotor resistance, torque current, excitation current, stator resistance, and so on. With the vector control, especially with the general purpose, for example, you get a significant increase in torque, and in fact, it is often appreciated. The advance instead, with which you can get 150% of torque at 1 Hz, is available for inverters that have the possibility to set the number of poles. The E700, E800, A800 and F800 inverters can do it. The tuning procedure is the same. I will only change the value. The parameter to perform the auto-tuning is 96. 96 can take various values. If I put the 11 value, it means that I want to perform a general purpose magnetic flux vector control auto-tuning. If I indicate the value 1, it means that I am going to perform an advanced magnetic flux vector control. If I want to define the value 101, I want to perform a dynamic advanced magnetic flux vector control, so not static. The FRA800, as you remember when I told you at the beginning, has the possibility to manage two motors. So with the RT signal, I can go and do two different tuning. In fact, you see the characteristics of the motors make a recipe change. I use other parameters to define a second motor that can also be totally different from the previous one. Then we move on the real sensorless vector control. This type of control is only available for FRE800 and FRA800 inverters. I get a 200% of torque at 0.3 Hz, very efficient in terms of control methodology. The procedure is always the same. I do the auto-tuning in advanced mode, and then I change a parameter. The parameter 800, which changes the control methodology. By changing that, I will pass and tell the inverter you will now work in real sensorless vector control. So the mode of piloting the motor itself is managed differently, increasing the performance exponentially, which we get the peak of performance with the vector control, which I remember to be a closed loop control. In fact, up here we talk about the FR8AP option. It is the encoder option, so it is an expansion to put where I can go and read the encoder mounted on the FRA800 and also on the FRE800. I remember the encoder must be loaded on the motor shaft, not following a reduction. Through the vector control, I can manage speed controls with torque limit, torque controls, and position control. In fact, the vector control has excellent motor management compared to the classic V on F, and sometimes it is compared to those of DC machines. We have talked about FR8AP, but what is an encoder? It is an angular or linear positional transducer, depending on how it is. There are two macro families, incremental or absolute, where absolute can be single rotation, multi-rotation, or programmable. Incremental encoder have n windows. In fact, the resolution given by 360 degrees divided by n, where n represent the number of windows. And it tells me the number of impulses that arrive. This is very useful because it gives me back, for example, the motor speed. Very important because I know outside the hypothetical frequency I am sending them. Because think without encoder, I say I am an inverter, I say to the motor, turn at 50 Hertz. So I guess he's doing the nominal 1500 revolutions, but if he's doing 1040 100 revolution, I don't know. With the encoder, however, know how. In fact, when inserting the encoder, there is a frequency compensation to compensate for the flow and everything else. I know if I tell you to do 1500 revolutions, it will be 1500 revolutions. Then, well, I have this little parentheses, or if I not, the absolute encoder, where I have such an encoder, it has the particularity of having n tracks, where for each track we have different binary compensation, where it gives me the precision of the absolute position in the rotation angle. The readable encoders from the inverter are of two types: line driver or classic open collector, where the signals are TTL rather than HTL. The differential is that usually is preferred the line driver, because it is less subject to disturbances, because it have the phases plus their negation. So A negated, B negated, zeta negated, unlike the classic open collector, which is A, B, and zeta. Obviously, we also define a maximum resolution, which is 4096 revolutions, readable and processable by this option that we can see here. The name is FR-A8AP. Below we can see our inputs, and I will bring my external power supply 5 volts if it is a TTL, rather than 24 volts if it were an open collector, and SD is my reference common. As far as the installation is concerned, it is very simple. There are simply two switches to pay attention to, where we have one where I define whether the type of encoder is of the line driver type rather than complementary, so open collector, and the other if I have to go and activate or not an internal resistance, which is defined whether it is step-by-step. If it is of the line driver, then on, or if it is of the open collector type, which must be turned off. To do an encoder calibration, first of all, you must be in V on F control, and not with the auto-tuning done. This because tuning itself already performs a compensation in frequency. So I don't know if the frequency is compensated by the encoder or by the tuning. So I put the inverter in V on F mode, and then I go to modify the parameter 369, then where I must put the resolution of the encoder. In the parameter 81, the number of poles of my motor, and in parameter 367, I perform this calculation, that is nominal speed minus real speed, for the number of poles and divided by 120. Once this is done, I run a test in PU, for example, at 5 Hz. And if I see that the frequency fluctuates, the encoder is read. If the frequency remains flat, it means that the encoder is not read and the options can be two. Or the sense of rotation is wrong, so you just have to turn on parameter 359 and bring it to 1 from 0 or from 0 to 1, or else if even with the or else you have wrong something in the wiring, and then you have to review something. As I was already telling you, the FRA 800, the FRF 800, and the FRE 800 inverters can handle PM motors. PM motors are not trivial to manage because unlike an asynchronous motors where I just give it a little voltage, a little frequency, and it turns, the PM motors must be calculated. It must be pre-parameterized with certain values where I have to put, for example, the inertia, the negative exponent of the inertia, the voltage induced on the windings, and so on. The PM motors are divided into two categories. The SPM motors, therefore with superficially magnets, or EPM motors with internal magnets. As a parameter, I have to define the nominal current in the parameter 9 and the type of engine of motor in the parameter 71. In the parameter 71, I will put 80, 83 if the motor is an EPM, or 90, 93 if the motor is an SPM. And obviously for the asynchronous motor, 3 or 13. If self-ventilated, 3. If servo-ventilated, 13. Then I compile the number of poles, the nominal power of the nominal power, the nominal voltage, and the frequency, the voltage induced on the windings, the inertia of the motors, and the negative exponent of the inertia of the motors. Once I have done this, I will perform the auto tuning, which is as I explained before, but here in this slide it is repeated. Once I have performed the tuning, it is ready to work. Now we will talk about communication. Communication are of different kinds. They can be serial or they can be Ethernet. Let's start with the serial. FRD700 and FRE700 are already on board, as I told you, have this RJ45 connector with which it is possible to manage serial communication. This is also available in the FRF 700 version now, but now it is out of production. The previous version of FRA 800 had this plugin that allow to communicate with a master, which can be, for example, PLC Mitsubishi Electric with Mitsubishi protocol, and command it. So, as you well know, the serial communication obviously requires parameterization, such as the station number, the baud rate, the string type, so the number of bits of the given length and the stop, the parity control, and possibly the communication waiting time, the CRLF control, and of course the protocol selection. I won't dwell on this topic too much. You just need to know that the inverters already have serial communication on board, so it will allow you to manage it completely, as if you were managing it from the outside. You can give frequency references, gear commands, you can change parameters, read the monitor, reset the inverter, clear the inverter. You can do whatever you want, but in terms of both in terms of the data and in terms of the serial communication. You can also manage the Mitsubishi protocol, like the slide that I am running very fast, and in terms of managing the Modbus RTU, which is also very simple. I already have some predefined register, and I just need to point them correctly, and the game is done. Another very important thing you need to know is that Mitsubishi Electric already offers you pre-made packages to make your work easier. For example, imagine you have purchased sorry, an inverter and an operation panel. We already have templates available for you to use and then customize in a function of your preferences. For the inverter management, let's look at this. At the GOT level, we have pages where I can change all the parameter. Just think about how long it would take you to manage all these parameters, counted correctly with the correct comment. For example, for an FR A800 inverter, which has around 1,000 parameters, let's say it takes some time. So all the parameters management, the possibility of making graphics, monitoring, commanding. For example, this is for an FRD, giving a forward speed, stopping it, giving a frequency here in RAM, seeing the status rather than making historical graphics. So you can also go with the cursor to see what happened over time. Going to see what I was already mentioning about the FRF 800, this diagnostic curve, where it gives me the values, where I can go and play around a little bit if I wanted to make the reading a little bit more complicated. The alarm history with the possibility of resetting the inverter, and the history itself, the life of the inverter, the life of the capacitors, if the fan works, and so on, all for 16 stations. As for Ethernet connection, there are different protocol. Obviously, you have to be able to communicate with all the possible networks available in this market. So, as far as the FRA800 and FRF800, there are several expansion. For example, the A8ATH, with which is possible to communicate in CC-Link IFL Basic and Modbus TCP, rather than the management of the A8 NCE, which is the CC-Link I-field that works at a speed of 1 gigabit. rather than the Profinet with the A8 NPRT2P card. I'm not talking about the E800 because you've already seen that there are already dedicated models. So the Profinet model, the Ethernet TP model, and so on. The same goes for the FRE 700, which you can buy the card, the option to have it, or you can already take the any version, where you have CC-Link, IFL Basic, and Modbus TCP/IP. Or you can buy this card, which is the A7 Net 2P, which is the multi-protocol card where inside there is a USB port on the card where you can set it up to communicate either in BACnet IP rather than CC-Link FL Basic or Ethernet IP, Profinet, and so on. As I was telling, all our inverters have a double safety channel. This safety channel, of course, manages mainly the STO, unlike the FRA700, which through the ProfiSafe or in any case the main safety communication bus can manage other functions, such as SS1, SBC, SLS, and so on. As you know, for safety, first of all, you have to define a safety plan divided into 7 steps, where you do the assignments, the risk reduction, the definition of safety requirements, the implementation, sorry, of functional safety system, the verification of safety, and the validation. Then you create a documentation related to a functional safety system to reach and with the verification of conformity. Once this is defined, you define the performance level and the seal. With the seal, you use these tables, which are defined by specific entities for safety validation to define the risk of the frequency, the probability of this event occurring, and the possibility of avoiding such risk. Once this is defined, you get an idea of what the seal and the PL are for you to work safely. Keep in mind that our inverter, as I said, are seal 2 and PLD, which is already a good level of safety, as shown by this table, PLD and seal 2. Obviously, the FR A800 inverter in SCE, so with the safety version, has PLA and SEAL 3, which is the most reachable. An example of connection is as follows. I go out from a 24 volt, which is the SC of FRD and FRE 700. I enter, for example, a safety relay, which I cut simultaneously S1 and S2. I have a minimal gap between the two, otherwise I make a mistake. So it is very important to keep this in mind. It must be simultaneous or for example, an FRA800 inverter, external power supply minus on safety input common, positive on a safety PLC, which can be a VS0, our safety PLC, rather than other cases like pills or something like that. I close on S1 and S2. I also manage the SO output for the reset management. I have finished with this. This is an example of TÜV certification for water connection. And with this, I have finished. Thank you all for your attention, and who knows, we might hear each other maybe at the level of support.